Somewhere in the sky right now, there's a patch of light so small you could cover it completely with a single grain of sand held at arm's length. Inside that tiny patch sits a faint red smudge that shouldn't exist, the kind of thing an astronomer would normally throw straight into the trash bin of bad data. Except it's not a mistake. It's real, it's confirmed, and it just forced scientists to admit something about the early universe doesn't add up. I'm Arif Hassan, and this is AH History. That faint red smudge has a name. MOM-Z14. That light left its home galaxy roughly 13.5 billion years ago. The universe itself is about 13.8 billion years old, so this light has been traveling for nearly the entire history of everything. It crossed a constantly expanding universe the whole way, which is exactly why its color shifted so dramatically toward red and infrared. And by the time it reached the James Webb Space Telescope's mirrors, it barely resembled visible light at all. When scientists finally measured it properly, they ran into a real problem. This galaxy is too bright, too small, and too chemically advanced for a point in cosmic history when almost nothing was supposed to exist yet. To understand why that matters, you need to picture what the early universe actually looked like. For its first few 100 million years, there were no galaxies, no stars, nothing to see at all. Just a thick, dim fog of hydrogen and helium expanding into darkness, a stretch astronomers call the cosmic dark ages. And the name is literal. That fog was so dense light couldn't travel freely through it. Eventually, gravity clumped denser pockets of gas together until they collapsed, heated up, and ignited into the first stars. Violent, short-lived, and intensely ultraviolet, stripping electrons from the surrounding hydrogen and burning clear bubbles into the fog. Those bubbles merged, the fog lifted, and that transition, called reionization, marks what we now call the cosmic dawn. Every deep-field telescope observation is, in some sense, trying to catch a glimpse of that sunrise. Until recently, the record for the most distant confirmed galaxy belonged to Jade's GS Z14-0, with a redshift of 14.18, corresponding to light that departed when the universe was about 290 million years old. Redshift measures how much the universe's expansion has stretched a light wave on its journey to us, and it functions almost like a clock. The higher the number, the earlier the light. Then a team led by astronomer Rohan Naidu, working with researchers from MIT, the University of Geneva, and collaborators, went back through existing Webb imaging data, specifically hunting for promising candidates other researchers might have passed over. They found an object visible at longer infrared wavelengths that essentially vanished at shorter ones, exactly the signature you'd expect from light so severely redshifted its entire blue end has been erased. In spring 2025, they pointed Webb directly at it and ran the light through NIRSpec, an instrument that splits incoming light into its individual wavelengths. The same basic principle as a prism splitting sunlight into a rainbow. The spectrum confirmed a redshift of 14.44, breaking the previous record. This light departed its galaxy roughly 280 million years after the Big Bang, when the universe had lived through only about 2% of its entire existence. To picture that scale, imagine compressing the universe's entire history into one calendar year. The Big Bang happens in the first instant of January 1st. This galaxy is already shining brightly by around January 7th. The dinosaurs don't show up until the day after Christmas. Every human being who has ever lived fits into the last few minutes before midnight on New Year's Eve. And we built a telescope, launched it roughly 1.5 million kilometers from Earth, and caught a single particle of light from the very first week of January. Here's where the real trouble starts. MOM-Z14 is tiny. Its visible extent spans only around 240 light-years across, compared to our own Milky Way's roughly 100,000 light-years, hundreds of times more compact than the galaxy we live in, closer in scale to a dense star cluster than a full galaxy. And despite being that small, it's absurdly bright, putting out far more light than anything that young and that compact should be able to produce under standard formation models, which predict early galaxies at this stage should look dim, messy, and slow to assemble. This one looks compact, mature, and intensely energetic, almost as if it skipped several stages of normal development. Scientists have proposed a few explanations, each with uncomfortable implications. Star formation in the extremely early universe might have been far more efficient than assumed, with gas collapsing into stars unusually quickly. Or the very first generation of stars may have been so massive and hot that relatively few of them could outshine an entire modern galaxy on their own. Or something else, potentially an extremely early black hole actively pulling in material, might be feeding energy from the galaxy's center. Any of these would require real revisions to how astronomers think the early universe worked. But the brightness isn't even the strangest detail. Researchers examining the full spectrum found a nitrogen-to-carbon ratio in the surrounding gas that came back unusually high. This matters because heavier elements aren't free. The universe began with almost nothing but hydrogen, helium, and a trace of lithium. And everything else, including carbon and nitrogen, had to be forged inside stars and then thrown back into space when those stars died. Building up a meaningfully enriched chemical environment normally takes multiple full generations of stars living, dying, and recycling their material. At only 280 million years old, there should barely have been time for one full stellar generation to complete that cycle, let alone enough to explain the chemical imbalance actually detected. There's a second strange layer here too. That same nitrogen-rich signature has been observed in globular clusters in our own cosmic neighborhood. Dense, ancient, spherical star clusters typically found orbiting galaxies like the Milky Way, generally treated as relics from the first few billion years of cosmic history. If MOM-Z14 already shows that same chemical fingerprint, it suggests whatever process builds structures like globular clusters may have started almost the moment the cosmic fog cleared, compressing the timeline in a way that's genuinely hard to explain. And this isn't an isolated case. Since Webb began full operations in 2022, it has repeatedly returned versions of this same surprising result. Galaxy after galaxy in the early universe turning out too luminous, too developed, and too chemically enriched for the moment in cosmic history we're catching it in. What started as a handful of rare exceptions has increasingly started to look like the standard result. That matters because our current framework for how cosmic structure assembles over time represents decades of careful observation and testing, and it has survived an enormous number of those tests. It's not simply wrong, but it keeps getting surprised in the same direction. And a model that keeps getting surprised consistently in one direction likely has a genuine gap somewhere, whether that's dark matter playing a more aggressive early role than current models account for, different underlying physics for that first generation of stars, or some mechanism from the universe's first 100 million years that hasn't been fully identified yet. That's not science failing, that's science running into real contradictory evidence and not looking away from it. Researchers involved have already said Webb appears capable of pushing this frontier even further, and this particular record likely won't stand for long. There's a separate, genuinely strange anomaly in Webb's broader deep field data worth mentioning, and researchers are still debating whether it connects to any of this. A separate team sorted a large sample of spiral galaxies in Webb's deep field images by which direction their arms wind, essentially which way each one spins. In a universe with no preferred direction, you'd expect roughly a 50-50 split. The count came back noticeably lopsided. One speculative explanation some researchers have floated, and it's genuinely a minority exploratory idea rather than an accepted conclusion, is a concept called black hole cosmology, the notion that our observable universe might itself sit inside the interior of a black hole formed in some larger parent universe, with the Big Bang representing the far side of that collapse, rather than an explosion into empty space. A much more mundane explanation is also on the table. The Milky Way's own motion through space can subtly brighten objects rotating against our direction of travel and dim those rotating with it. So an inaccuracy in our estimate of that motion could introduce a real statistical bias without requiring any deep cosmic mystery at all. Small sample sizes and early measurements can also simply get revised as more data comes in. The honest position isn't that our universe existing inside a black hole has been proven, and it isn't that the idea is nonsense either. It's that several separate pieces of evidence, a galaxy that formed too quickly, chemical enrichment that arrived too early, and a section of sky with a strangely lopsided spin, are all pointing in a similarly uncomfortable direction at the same time. Roughly 13.5 billion years ago, that faint red smear of light left its home galaxy, carrying a genuine question we still can't fully answer. And it just told us we currently understand considerably less about the early universe than most scientists confidently assumed a few years ago. If deep space mysteries like this genuinely interest you, Follow this channel, because we cover findings straight from real published research, explained clearly, without unnecessary exaggeration.